Yeah, let's continue then with chapter 2. So Gustavo's going to present. Okay.
So, just like you said, present the second chapter of the book that we'll talk about Brownian motion. And I'll be following the same sections that the book does. So we'll start by talking about Pre-Brownian motion. That is a kind of version of Brownian motion that doesn't need to be a continuous path. After that, we move to explore this continuity to define properly the Brownian motion. And finally, there are some things about this strong Markov property, but I don't think we'll get to there today. Well, and of course, my English may not be the best, so if something is unclear, please tell me. So we'll start now with the definition of Pre-Brownian motion. Here, well, it's defined as like this. So just to remember, if we have that use a Gaussian with noise on air pulse, whose intensity is like the Lebesgue measure. If someone doesn't remember what that is, it's just that G would be some mapping that takes some functions that belongs to the Q in mega. I think they write like this in the book, and if you from here F that belongs to the center Gaussian. Okay. So we'll define our Pre-Brownian motion to be a random process vectored by a T such that it's the Gaussian noise based upon this indicatrix from 0 to T. Right, and the first characteristic we will see about this is that this Pre-Brownian motion will always have this covariance. So it's easy for the thing to do. So just by the definition of the wing noise, we'll have that in particular the statement of V of negative continuity times this. Okay, just directly the integral of the indicative, the multiplication of the both indicative and x, and this will be directly the minimum between just those two parameters. They also use this notation in the book. To be honest, I didn't really understand how they use it, because in this equality they write something like not.
I think it means notation.
Yeah.
Because it's not and then period.
It's okay. So yeah, I wasn't sure because okay,
it's not this.
Yeah. Which of that they use that and I didn't use. Okay, so that's the first characteristic we have. And more complete definition maybe or characterization, I don't know, is this. So here we have in fact not 3 but more ways of defining this Pre-Brownian motion. We have the original one. Okay, the one that comes from the first slide. That will be equivalent to saying that okay, we have a Gaussian process with this covariance that is something we just showed, And there is a third that says, okay, x0 will be 0 arbitrarily, and for every choice of s and t, this random variable, is independent of basically of the history of everything that's happened until we get to s, the first step. And it distributes according to this normal centering 0 with the variance. So we'll check that. And also that can be modified into a fourth version that I forgot to write that, but it's exactly the same. I'll write that when I want to show that the third implies the first. Okay. Okay, so we're ready. This silence is what we could show. Now, we want to show to prove that these also happen. So I need this just because sometimes I forget. So okay, the very first thing is this, and since we have that x0 will distribute according to this, it's clear to see that it will be 0 arbitrarily. And then for the second part, we'll define two ends. So we'll have hs and h capital S, and this will be so hs will be the vector space spanned by all the processes before reaching the x of s, and this will be, instead of that, will be kind of the same, but in this case spanned by x, let's say x plus u, I think they use, minus xs for u greater or equal to 0. So and now we have the what's already happened and all the places we can move from where we are right now. And we want to show that these two will be independent. So we want to show that these two will be independent. That thanks to a theorem we have from the first chapter is just the same that proving that these two are orthogonal. So we can see that just from calculating the difference of the x squared times x plus u minus s for any fixed L and U. This would be the norm. So here just multiply. Here we have x L times x L minus so plus U minus x L times x L. By the linearity of the expression, we'll have then it is U. And from what we said, we already said, this will be just the covariance of this, so will be the minimum between R and S plus U, but since R is smaller than S and this is positive, we will have that this is just R minus, same way here, R is smaller than S, so we'll have this is R minus R, and it will be 0. So it will be, they are going to be orthogonal, therefore the events are going to be independent. And since they are independent, we can just use the arithmetic of the normal processes just to get the part here that this distributes according to a normal with a variance that is just a different the difference of the variances. Okay. And we also have to show now that the third, I'll go through with this. Yeah. And now what's left is that we must prove that the third one implies the first one. So, where is this?
Gonna use 4,
Yeah, that's
which is
what
not
I-
written, but
so
it's
in-
extension of 3 when you just partition
Yeah, I'm
in
just
multiple intervals. right?
I'm going to write it here because I forgot to put that there. So we have a first version of this that is just saying that we have an x0 that will be 0 unfairly. So this is how also given the relative of this. And then for any choice we can make of T0, you got T0, smaller than T1, smaller than T2, like that until T getting the use. We'll always have that xi minus xi minus 1 distributes like a normal with increments. Yeah, answer. It is for ti c and minus 1. So this is going to distribute just like this. It's the same that it states in that. And also we'll have that it's going to be independent or of any other of the process. Okay, so let me yeah, it's independent of the other differences and the any other process we can define. So this is very straightforward from the third, and it's what I'm going to use now to prove that what that 4 implies the first one. So how I'm going to prove it, I'll use T to define that I can have a Gaussian noise that defines this. I'll use this to define
Gaussian process. A Gaussian process?
Yeah, a Gaussian process that will be the Gaussian noise that allows us to say that this is a Pre-Brownian motion. So I'll define the mapping G for that goes from from L2 to the Gaussian center space, like the following. I'll define first G for F, where F is, I think it's, I don't know what we call it, but it's ways.
This way is constant. Is it
Step function. Sorry.
step function?
Yeah. Function. So this will be defined like the sum over n over e. Okay, so given a step function that is going to look something like this, fix lambda for any of the steps that we're taking, I'll define the mapping just like the very same functions, but instead of taking the indicatrix here, I'll take just the difference of the noise in that step.
So that's a parenthesis, not an absolute value.
No, it's sorry, it's absolute value.
It's absolute value. Okay.
Yeah. So no, I'm not sorry. Yes, it's the one.
Okay.
Yeah, I thought it wasn't. Okay. And what we have is that if I have two step functions, let's say alpha equal G, that is defined over the same interval, like E, I'm not using knowledge here, mu sub E indicative. So what I will have is that this way of mapping this will gives us that if I take what will be the norm of this, the norm between sorry, like the inner product of the between the two mappings still is going to be that, right, the integral of f and g just by the definition of the data with I just narrate that, which is just the inner product of f and g. And the point of this is that since this is a isometric, isometric,
An isometry.
yes, isometry, we can extend this in a way that it's going to be an isometry between the L2 space, to the full L2 space, to the Gaussian center space. Why we don't have that restricted from here? Because we are using the step function, but they are going to be dancing the L2, so that can be extended. So again, we have therefore that this is Gaussian noise, and because of like the obvious reasons, I think everything is going to be Gaussian here, and it's easy to see that it accomplished the very first definition of the Pre-Brownian motion.
I mean, what matters is that you have Gaussian noise and the intensity is the Lebesgue mesh.
Yeah.
And
So
that's yeah.
Well, the first corollary is that given a Pre-Brownian motion B, then for every choice of G1 to Gn as its density. So that's also something that's pretty straightforward. We can, to make this easier, we can just instead of calculating this probability, we just calculate x1 and the probability of x2 minus x1 and so forth. And since they are all independent, we just have the multiplication of everything. Also, something that is very straightforward, since we have a Pre-Brownian motion, it's going to be symmetric. So we have minus the Pre-Brownian motion. It is still a Pre-Brownian motion. It can be scaled by positive values. So for every lambda that's positive, we have that this process is out Pre-Brownian. And something also very important is that in this case, we can, for example, for like something I think I already said, but we can forget a little bit about the path of the whole process. So any step we take, all the process that goes after that, it is still a Pre-Brownian motion by itself. No, until now, okay, we have a little properties, but we want to set a motion that will be continuous. So we'll make some arrangement to see that even when what a Pre-Brownian motion is not exactly continuous, we can modify it a little bit. So we'll define what's the sample path. So let x be a random process with values in E, where E is a metric space. The sample paths of x are the mappings that they take one t in some interval or some index, and it maps to the t to a realization in the omega or in the sample space. Okay. That's what we'll define.
So the sample path is a random variable that depends on omega, and it gives you the whole trajectory or the whole function xt of omega.
Yeah. So we'll want to use some modifications. The plan is that to find some continuous path, we're going to have some sample path from a Pre-Brownian motion that is not necessarily continuous. And we'll use a modification to set a sample path now, but that it's actually continuous. So what's a modification is just that if we have two random processes, indexes but the same index, index t, well, the main idea is that they are always the same. The probability that they are the same, it's one in every point of the index set. And also we'll have this property here that it's, to me, it's kind of hard to say this word, but so the process takes that.
I have a question, because is there an issue with the parentheses in the definition of modification? Like you want, like that parenthesis should be outside of every. Is it, you're asking for every time that the probability of this sample path at t is equal to 1? It's like a pointwise in time. Is the whole trajectory, or is it the whole trajectory? Maybe it's fine. I'm just trying to grasp the. Oh no, it's fine. The definition is for every single time that probability has, like that event has probability 1. Okay.
Okay. Here we say that two processes are indistinguishable. If kind of the same idea that they are the same in every point, but in a set that is negligible. They are measure 0. So this is kind of the same idea, not exactly the same, but the statement that they say in the book is that if we have that these two are continuous, they are exactly the same. So two processes are indistinguishable if and only if they are a modification of the other.
I mean, indistinguishability is a stronger, right? Because you're incorporating in this negligible set that simultaneously on every time you have this equality. I see.
The difference is that the for all t is inside the parentheses. in the second.
Yes. And that was my first thought about the first definition. They're actually different. Do they explain in the book why these two things coincide in the case the XTs are always
It's-
continuous
Uh,
or not?
I think they say that can be proved, but.
Can be proved, okay,
But,
because I read the chapter, but I went up to that point, so.
so. But it
The book makes a small remark saying that what I said. Just put the row inside the parentheses. Say this formulation is slightly incorrect since the set for all t.
It's not necessarily a measurable set.
It's not necessarily measurable.
But this first thing is well defined, this one is not an issue, right?
So this one is correct.
Yeah.
Yes, I think that is why the definition is stated like that.
So, with that, I think that, no. Okay, so with that, we'll use the Kolmogorov's lemma, so we'll have the first idea of a continuous path. So what it says is that let x be a random process indexed by on the interval I subset of the real numbers and taking values in a complete metric space. If we have an epsilon q and capital C such that they have this, that for any s and t in the interval, we can bound the expectation like that. Then we'll have a modification of the original process with samples are other continuous with exponential. Okay,
There is exponent q means. No, just a type.
yes,
It's
yes,
the expected value of the distance to the power of q.
Yeah.
That's what it's actually.
so
Me, it's fine because. That's what they say.
they also state this like in a way, it's like this. I don't know if I also in the hearing that, but it's supposed to be in the same like this, that for every alpha, there is a constant T alpha such that we'll have this modification that's going to be continuous in this.
Is this D the same D that it was before? It's just,
The distance on the metric space.
Yeah.
um,
But
Okay.
we'll check.
okay.
We'll check. So. Where is that? So the way that the proof goes is that we'll use the original random process and this bound to say that we can have some kind of some kind of color continuity between in a dense set here in the interval, but not necessarily in the whole interval. So we'll take some limit of the places where we can have discontinuity and then generate the modification. So we'll start by showing we'll have the color continuity in the dyadic the dyadic interval. I don't know how that so the first thing they do in the proof is that they proof is that the probability of the distance of an FT being greater than A. It's going to be bounded using this. We just have to use the Markov inequality. So since this is greater or equal to 0, this will be the tenth writing the probability between these the probability of this being greater than this. Okay, and therefore it will be smaller than the expectation of this, that's going to be smaller than that, so this would be C C minus that to the 1 minus 1 plus epsilon divided on A3. Okay, so we will have this down that we'll also use. And then we'll use the dyadic numbers to explore this process. So we'll take the probability of in this case, instead of taking randomness and T and taking the dyadic interval for E from 0 to from 1 to N. And I'm using this as the A here just because at the end this will tell that the probability is going to 0. So it's something easy to work with. So in here we'll have that this probability is going to be smaller than what we have here. So this will be from C. Here we'll have 2 to the N. Sorry, minus alpha and then times 1 plus epsilon divided by, in this case, into the minus n.
So that
This goes away, and this is just alpha plus epsilon. Sorry, I think I missed something there.
I mean, the length of the interval is to the
Yeah.
exponent q, right?
So, yeah, I missed that. You.
Q alpha, right?
Yeah.
And then the other term comes from the distance, which is just 2 to the minus n times 1 plus epsilon, right?
Okay, so this is for just one of the intervals, but
There's, I think that 2 to the nq alpha, it's with a positive exponent rather than negative. Because it's 1 over a above,
yeah,
and you're applying that to 2 to the minus n alpha. So you get, yes.
yeah, sorry. But now we'll, okay, this is just for one interval. We'll see that the probability will change. The union of this, the one correct author. We can balance that using the union command. So this will be just 2 to the n times C times Q into alpha to and this case please and minus 30. Right, so this one goes away and this one also goes up. And we're left with just which we can write also like n times q minus alpha, sorry, times alpha minus epsilon, where this is going to be negative since that's the assumption says that alpha is somewhere between 0 and epsilon over epsilon over t. Right, so this will be, in particular, this is going to be bounded and not bounded, but big. So given that the union of all of these events as probability that is founded, we can use the Bernoulli lemma that it's going to say us that with probability G1 we have that there is just finite quantity of times where this happens. Okay.
Not just that, right? The fact is like this is also a summable sequence. So for using Borel-Cantelli, you need to add up these probabilities of events. Right? So it's not just that it's finite, but the summation is going to be finite. It's fine. Yeah, and then you will conclude this this other statement.
So people are going to be there. Right. So, all right, team. Then we have that. Okay, so we'll conclude from the Bernoulli lemma that we will have significant quantity of cases where this is false, but okay, there will be just a finite case in the majority of in the most of the cases there this is going to be true, right? So they define them the E of alpha. So they define this K of alpha omega to be the supremum of over n of the supremum over I of the distance in here that it's going to be bounded with probability one, not necessarily always, but with probability one, since it's bounded for every n greater than n0, and for the cases that n is smaller, it's also bounded because they will be thin. So that is bounded. And here they use other lemma, but it's a lemma that they will have to talk, but I'll just use it like that. That thanks to we'll be able to say that here and it's smaller equal to u alpha alpha with of alpha equal to okay, so they use our lemma to say that with this and so they use this lemma that you can see in the book because we never really have that much of them, but they use it to say, okay, since we have that this is going to be bounded, we are going to be able to say that the distance between that the step we take in from xs to xt is going to be bounded by this. So we have some kind of continuity, but just in the cases that S and T belong to the set T, that it's the set of the dyadic numbers, so they can be written like something like I times 1 divided by 2 to the n for some n, and so on. So we have that we can set something like a Holder continuity, but just in this place that is going to be dense, but not the full interval. So we're going to take some modification that's going to be the x hat. So it gets to be completely continuous, and we're defining that like just let's be 0. Write this a bit more to the left. Okay, so the modification we'll take is just that we'll define x to be around the portal such that if this k alpha it's not bounded, it's infinite, it's going to be x0 that we can fix. It can be anything, but this, thanks to what we said with the Mercantile lemma, this is going to help me just negligible quantity of time, so it doesn't really matter like that. And in the other cases, we'll use that the process will be the limit of the original process, but using the approximation that is given by the diagonal. So the ones that we can use.
So finally.
So, okay, by the definition, we'll have already that. Thanks. So here we need to put that this is a modification of x. So then here's the so I think I forgot how they wrote the modification stuff.
This is true because of the Markov inequality for eliciting probability.
Yeah.
This is just Markov inequality from the hypothesis of the theorem. They was reading the same. I don't see how they.
Sorry, I'm confused. So you constructed this thing is Taylor continuous
But
with probability 1, right? I mean, or not, surely, like, you built it this way.
Yeah.
But you want to prove now the property of,
But it is a
modification.
that is not just.
so you
any
fix
pro-
t, and you
Yeah.
want to see that the probability of xt being equal to x tilde t is 1.
Yeah.
You have that property certainly for static numbers, I suppose.
Yeah.
I think that we finished that part.
Yeah.
Like, now you.
Yeah.
Now you see. That
I was just trying to prove the fact that it is a modification.
yeah, you need to prove that x tilde t is equal to xt, almost sure.
Almost sure.
And you have this equality with improbability. This equality is improbability. Now you need something more.
An increasing sequence, I think, implies convergence almost sure. Like,
I don't know if it is increasing. But it says here,
so much
I'm not sure. It's the uniqueness of the limiting probability. That's the conclusion. Because by construction, you have that x tilde t is the almost sure limit of xs. Yeah. And then now this is the limiting probability. Then the limiting probability of x tilde t is also xt. And then the uniqueness of the improbability limit gives the conclusion. I believe it's that. It is written weirdly. I agree. Yeah.
Yeah.
Is that, no? But
I think so. Yeah, I mean, it's kind of what they. Yeah, but they don't say a lot, but. They just take the, like, the limits in the variety going to be the limits.
What do you mean here by limiting probability?
this is true improbability in this case.
What does that statement mean? That the probability of this is 1?
No, improbability. That the measure for all epsilon, the probability of being
Okay.
greater
That's what
than
it
epsilon, and this is given by the Markov inequality in the original hypothesis.
Yeah.
And then you can conclude that this is improbability. That's true. You replace xs by x tilde s. This is true almost sure. And this is true improbability then. And now you have the uniqueness of the limit improbability. And that's the conclusion, and therefore you have,
They have
you have,
There you call them.
the still that is
I see. Okay,
Okay.
maybe it's too tedious to write it down, but yeah, okay.
I think that who's the legal here goes a little bit bored, you know, like,
Yeah.
it is a confused word.
Okay, so.
And the lemma is left to the reader, right? Let's-
Yeah. They also prove the lemma, but it's just.
No, we can look it up at home. It's our homework.
Well, with that. Then we have our first notion of continuity in pre-Brownian motion, so we have that since we have a pre-Brownian motion. The process will always have a modification sample, the sample path are continuous, you know, locally hold are continuous with that exponent is that 1/2 minus delta. And then we'll have the definition of the Brownian motion. That it's going to be a process of that is first pre-Brownian motion and those samples paths are
So is it clear that a modification of pre-Brownian motion is also pre-Brownian motion, I guess?
sorry, what?
Because you take a pre-Brownian motion and you
Yeah.
modify it so that it has continuous paths. And I assume that it's obvious that what you get here is also a pre-Brownian motion. Right? Because that only relates to the isometry property, right?
Even Juan Pablo proved that the limits of Gaussian.
I think that this is the definition, you're asking the
Yeah.
path to be continuous.
No, I understand, but what I'm trying to say is like what you just proved tells us that a modification of pre-Brownian motion is gonna be a Brownian motion.
Yeah.
Is that obvious? That's my question.
From any pre-Brownian motion will have a modification that's going to be Brownian.
But you
Yes, and my question is if whether this first property is already satisfied with them.
No, because you need that the expected distance be bounded by t minus s to the power 1 plus epsilon, with epsilon strictly positive. In order to get, go a little bit backwards with.
But we know that,
There,
we
you
know
don't have this necessarily with pre-Brownian motion, that's my guess.
if you start with the Lebesgue measure, yes. You do have.
With plus epsilon, should say without the epsilon. I don't know, I'm just guessing, but.
No, because this is to exponent q. It was missing. You can always play with it to make it true, and particularly this property of the variance is what's gonna give you this, right?
Yeah.
But I had a more basic question. We can skip it, no,
Yeah.
we can discuss it later.
Really understand what exactly what so that's the first definition of Brownian motion. And here we start with the third subsection. But I don't think
Maybe it's a good time to stop. Or, yeah, okay, so in 2 weeks.